A-level / GCSE physics, particles and radiation. So as usual, this half is going to be like flashcards, this half is going to be like explanation and explaining things. So first of all, atoms are made up of three main, I'm not going to call them organelle, things. These are the proton, the neutron and the electron. Before, you're used to saying that the proton has a mass of 1, a charge of +1, and that is it. You're used to saying the electron has a mass of 1/2000 and a charge of -1. And you're used to saying a neutron has a charge of 0 and a mass of 1. Well, that changes, because now you have to learn that protons have a charge of 1.6 times 10 to the -19. Neutrons have a charge of 1.6 times 10 to the -19. But that is a minus, so it's minus 1.6. And neutrons, surprise surprise, have a charge of 0. But as far as the mass goes, there is a difference now, and the difference is that all of them actually change. So the proton is 1.67 times 10 to the -27. The electron is 9.11 times 10 to the -31, and the neutron is now 1.67 times 10 to the -27. So they're very small quantities. If you want to know, like, the units is coulombs and kilograms. So what do you do with these? You do the specific charge. The formula for the specific charge is the charge divided by mass, and the what's this called? It's the units for this would be coulombs, and then kg to the power of -1, because -1 kind of equals that. So now, protons, neutrons and electrons. So when you're using them in specific charge, make sure you read the question, because obviously there could be questions with ions and there could be questions with nucleuses. So when you use ions, you obviously use the charge. So the charge could be a minus number, because an ion may have more protons than it, more neutrons than it does protons, and in that case that would mean that obviously it would be a negative. So now, proton number, this would be the amount of protons in an atom, and this number never changes, whereas the nucleon number, or the mass number, this would be the amount of neutrons and protons in the atom. And this leads me nicely on to isotopes. This is when the amount of neutrons in an atom has changed. So the element is the same, but the nuclide is different. And because we have isotopes, obviously there are a few isotopes that you actually need to know. So the isotope you need to know is carbon 14, and this would be the one to be able to measure age of a. It'll be able to measure the age of a dead thing. So basically, when we're alive, we take in carbon-14 atoms into our mouth, and then over time, when we die, we no longer do that. So the carbon-14 atoms decay, and then over time it goes through half-lives, and thus scientists can find out how old we are. Simple. So now, stable and unstable nuclei. So, strong nuclear force. This would be the force which would hold protons and neutrons together. This would have the exchange particle gluons, and would only work between the distance of 1, 2, 3 FM, that's femtometers. And why that is basically at 0.5 it becomes repulsive, because at that point the protons are really close together, and as they have the same charge, they'll repel one another. And at the point of 3 FM, the exchange particle, the fundamental force electromagnetism, would become too powerful, and thus would mean that it would repel anyway. So decay, alpha decay, this would be a helium nuclide. Alpha decay would be a helium nuclide. The mass number would go down by 4, and the atomic number would go down by 2. Whereas in beta decay, this would be the equivalent of adding an electron. So the proton, well, this would be equivalent of adding a proton, but so the proton number goes up, because like obviously beta or beta is a literal electron, but obviously there are issues of it's not actually, because the proton's changing. So yes or no. But in beta decay, this called for the anti-neutrino to be discovered, as it was found out charge is not conserved throughout. So because of that, a neutrino was made to be able to justify all of this. So antiparticles. So the antiparticles are positrons. It is the anti-proton, the anti-electron, the anti-neutron, and obviously the neutrino and the anti-neutrino. So obviously inside positron, anti-electron, anti-electron. Oh no. Anti-proton. These are all the opposites, so they have the opposite charge, they have the same mass, and that is all you need to know about them, apart from the fact that annihilation, this is when two antiparticle pairs hit / attract / meet, and this causes 2 gamma photons to be made, and the opposite is pair production, and this is when 1 photon would spontaneously convert into a pair, that is an antiparticle particle pair. So that is the first easy bit of this in a way. There is, what else is there? There is particle interactions, so we'll do that next. Particle interactions, these are with the 4 fundamental forces. So the 4 fundamental forces are strong nuclear, weak nuclear, electromagnetic, and then gravity. So these have the exchange particles of a gluon, of the boisons, so W boson, I think that's how you pronounce the word, I don't actually care. This has the virtual photon, and then gravity has the graviton. Simple. So exchange particles, well, we should probably write this down. Exchange particles carry around energy and momentum between the particles. Simple. So that is basically all we need to know about exchange particles. So this is the first part. The next part is all of the byrons, quarks, antiquarks, etc. So that would be part 2, I guess.